Hurrah, thank you. Right, so I spent a weekend away a few weeks ago with some school friends I hadn't seen for years, and I had thought of myself as a reasonably good cook, and we all took it in turns to cook, and the first 2 nights the meals were amazing, and I felt, by the time it was my turn to cook, I felt really nervous, and that's how I feel now, so So I'm going to talk about the Haskell Interface to Sundials and how easy it is, or how much easier it is to use inline-c rather than it is to use the traditional foreign function interface that's been around for donkeys years. So this is I'm going to talk about ODEs and how to solve them. I'm going to talk about my little implementation. I'm just going to do a very simple example of how inline-c does things. I'm not going to explain inline-c, so this is sort of like a worm's eye view, a user's view of how to use inline-c. So I'm not going to, there's some good talks. There's a video of Francesco, who wrote inline-c, explaining how it works. So if you want further details, I'll come on to that. If you want further details, you can go and look at that. And then some thoughts and, as I said, some links and the video to Francesco. So the idea is just to show you that you can get going very quickly. So you can have a very big C package, but you can actually start using it in Haskell very, very quickly, and go ahead and build your own. I don't know what you guys used. Did you use FFI or did you use
EU metaphor and
okay. So a bit about what the tool will cover. So why. There's already an existing package, I'll pull it from it again. Why change it? A brief overview, I've already said that, and some bits of my implementation, but certainly not all. So the GNU Scientific Library covers a lot of things. So it does vectors, matrices, linear algebra, Chebyshev, root finding, loads and loads of stuff. But one of the things it does do, for the projects I've been working on for the last year and a bit, is it solves systems of ODEs, ordinary differential equations. And we've had the benefit of that in Haskell for the last 11 years in H-matrix. So H-matrix gives you a binding, H-matrix dash GSL gives you a binding to quite a lot of GSL, the GNU Scientific Library, but not all of it. And that allows you to solve systems of differential equations. So why create another one? Surely the GNU Scientific Library is good enough. Well, not if you're a commercial company, sadly, because lawyers don't like GPL. And so if you want to sell your software, you're going to run into trouble. GSL doesn't have great diagnostics. So if your system of equations you're trying to solve runs into trouble, for example, if the step size, for the variable step size methods, if the step size gets less than floating point precision and it gives up, the GSL library just gives up, and you don't really understand why it's given up. And Sundials give you all sorts of information about how many, if you're using an implicit method, how many iterations it took to find the solution to the solution using the implicit method. So you get lots and lots of information. So if you're a modeler, it's great because then you can understand what's wrong with your model and do something about it. The other thing that Sundials does is it will find roots. So if you're, let's say you're modelling someone's blood sugar and you want to give them an injection of insulin every time their blood sugar drops below a certain value, you can't do that with GSL. Not even, well, no, I don't think you can, not even easily. Whereas Sundials, you can just say, tell me when the blood sugar goes below 10, and I'll give you, and then you can reset things and carry on the calculation. And performance, so we found Sundials it seemed to speed our calculation by 2 or 3 times, so we're very, very happy. So we're very happy with it, and it's got loads more methods. So GNU Scientific Library's got a very limited set of methods. The LLM the LLNL Sundials. It's got lots of methods, and I think you can even sort of give it a tableau that describes the method you want to use, and it will go off and use your tableau. So it contains a lot more stuff that I have never touched. So I've only ever touched the CV and the ARK and the cutter methods. But it also gives you want to look at the sensitivity of your solutions. It's got a suite to do that, and it's got things I don't even understand, differential algebraic equations. So, and it's been around for a long time and comes out of the Lawrence Livermore National Laboratory. Well, here in America, yes. We are in America. So here's a very, very simple example of something you might want to do in solve. So this is the red system. This is a very well-known system of differential equations that's got a chaotic solution. So it's interesting from lots of points of view. So here we are, and here's how you might get. And here in Haskell is how you might describe that. But it's written in a form that allows H matrix to solve it. I'll show you how to do that in a moment. So it's just got H matrix has got some very high level methods. So you can either just let it choose all the defaults for you. So you can just say, here's my equation, the Lorentz equation I showed you before. Here's my starting conditions, and here are the times I want you to give me solutions for. But if you don't like the particular defaults, then you can use a lower level function that gives you access to how is it a variable step size, is it a fixed step size, which method you want to use, and a few other things as well. And that's all to say. And here, I mean, if anyone has seen pictures, I'm sure you've seen pictures of the Lorentz system solutions, showing the chaotic nature, how it'll stay in one place and then suddenly switch to oscillate or orbiting another part of the phase space. Right, so that's so I'm just setting the scene there. That's the sort of thing we want to be able to do, is solve those sorts of equations and not reinvent the wheel. So we don't want to write lots and lots of solvers ourselves, especially when there are so many pitfalls in solving differential equations that people at Lawrence Livermore or people in the GNU Scientific, whoever's written the GNU Scientific Library, they've solved all those problems. You don't want to be trying to solve all those problems yourself. So if you want to write an interface to Sundials, the sort of traditional way of using Haskell has been around for 15 years, probably even longer, the foreign function interface. What you do is, for every C function in the library, you write something like this, and it gives you a very low-level interface to that function. Right? So you've now got, using the foreign function interface, but that's very low level and not something you really want to expose to a user. You'd really like to use the existing interface. And Sundials is very big. Right? There's lots and lots of functions in there that I haven't even looked at, and I haven't so far needed to use. But you don't really want to write lots and lots of functions yourself. So lots and lots of FFI declarations to all those functions. But I believe, I've never looked at it, I've looked at their sort of web page, but I haven't looked into it in detail. The OCaml people have written something that allows you to do pretty much what I described. So I think you have an OCaml, in OCaml you can actually call all the low-level functions in Sundials. But you don't really I didn't really want to spend a lot of time before we knew anything about Sundials, or had got very familiar with Sundials, writing a very lengthy set of, and then building up on top of that the interface. So using inline-c, you can actually just do you can just try out very tiny examples yourself without very much work, rather than having to do all this hard work. And the easiest thing I thought we should start with was, well, and for the company I was working for, they didn't want to have to rewrite their code, so I just thought the easiest thing to do was create an interface to Sundials that looked exactly like the interface to GSL. So this is like the one-slide introduction to inline-c. So here you are. You want to call a function to create a bit of memory that Sundials uses further on, and you're going to say you give it a parameter, say use the Newton method, but you don't know which other method you want to use with it. So what you can say in Haskell is create a variable named method which has a value 2, anti-quote it inside the C. So this is quasi-quoted C. So this is your C that works, calls the Sundials library and returns a result. In this case here. But you can pass in stuff from Haskell as well as getting stuff out from Haskell. So the anti-quotation, this is called anti-quotation, so you're allowed to pass in Haskell variables, and it indicates the variable method that we want to capture from outside the C. And inline-c actually goes away and does some type checking for you, so you can't just sort of, if CVO ODE create wanted a double there, and you pass it in, you get a type. So in the compilation phase, you get a type error. In the C, at the C level, not at the Haskell level. Inline-c also gives you a way of mapping backwards and forwards between C and Haskell types. So some of, not obviously not all. And you can define your error, which I'll come on to because I needed to do that. So here's an example. So in Haskell we've got the empty type, in C you've got the void type, you've got characters mapped to characters, you've got ints mapped to ints, etc. So you've got all the sort of standard C types, I guess, available to you as a Haskell program. But Sundials uses two structures. Something called a vector, generic vector and generic sum matrix, and it hides this information from you. And you're supposed to get this information from quite a big interface, right? So I didn't want to do that, so I cheated, and I looked at the for a specific implementation. So the idea is, sorry, I should have said, the idea is you might want to use a serial interface to Sundials, or you might want to use the multiprocessor interfaces. So there's MPI, there's other methods, so you can do all sorts of clever stuff with Sundials, far more than GSL. GSL can't do multi-processor, parallel stuff. So I define these structures in C myself. But it ties you to particular bits of Sundials. So it tied me to the serial interface, and it's also tied me to dense matrices. But to be honest, that didn't matter when I was getting started. So now that I need to be able to, a way in Haskell to get hold of this was to be able to put things into the matrix and to be able to get things out of the matrix. So I've created a Haskell type, the number of rows, the number of columns, and everything's a double in my world. And then I can create a storable instance of H matrix with peek and poke, and I then create a new mapping between my types and the C types, and then create this what's called a context. So this is all available to you in the inline-c package. And then when you want to use it, you declare the contexts that are given to you. So these three contexts here are given to you by the inline-c package. And then I added my own context that I created. And now all this is available to you in inline-c, in your program. So here's like the Jacobian in Haskell. So there would be some code there defining what the Jacobian looks like. But it'd be a pointer to my sum. So I just realised this is an old version of the code. So I've got rid of all the T dots. So you can do things with the vectors in Haskell. So you can set up this function in Haskell, but then you can say, well, in the C, anti-quoting is there a Jacobian variable, which has to be an integer. I thought it had to be an integer because I thought C didn't have Boolean type, so it had to be 0 or not 0, isn't it? And then you set a Jacobian with your function. The function, the $fun is available from the function context, and then you call this function with your Jacobian being passed in here, but it's got this C type, right, so, and everything works. So that's how I used it. Right? So I was able to pass in the function I wanted to solve. I was able to pass in the Jacobian. We had one. I was able to. We want to if the as I was saying, if the blood sugar hits a certain level, we want to be able to restart the solver. We were able to do all that. I just wanted to say, so that's pretty much it really. So it's very, very simple to use, I found. And that's how I used it to solve systems of differential equations. So nothing very exciting, except it's quite, so the main message is quite easy. I did get caught out a few times, so obviously you're in the world of C now, so you can't just think there's a garbage collector around, so you must free all your memory. And I did get caught up, I should have covered that up, and should have guessed what if you coerce a vector of 1 and 2 into the vector of int. That was so there is a ticket on that, but opinion seems to be divided on whether this should be fixed or not. I couldn't see why opinion was divided on that.
So what is the bug? Should it be a type error or should we give a different result?
I think it should be a type error. Well, either a type error or it should be 1 and 2.
So which would you prefer?
Sorry? Well, I prefer it to work properly. Yes.
I think it must be type error because coerce can't do anything about the data. That's the idea. Coerce must always use only the pointers and not the data.
Right.
Because it's supposed to be zero cost.
It's supposed to be zero cost, yeah. So yeah, a type error would be nice.
That would be the nice thing.
Yeah.
Actually, what's the representation of C in this case? Because
Of C int, I think it's we had it before, didn't we?
Has this happened because it thought they were double, and so that's what 1 and 2 work out to be in actually, or?
I don't think so.
The C that had in GHC is just a pointer to an actual
Yeah.
int somewhere.
I mean, we're talking about int here, so I didn't. Yeah.
Yes, but the int type is kind of inline into the pointer itself.
Anyway, sorry, I didn't want to maybe that was a surprise. So those are the two things one has to sort of worry about. I would hope this one would go away. And so there's quite a lot of information around. There's quite a good blog at the FP Complete site. The code itself on GitHub if you want to play, contribute. Inline-c's there. I wish I didn't know about someone had already written a really nice interface to OpenCV using inline-c. I wish I'd seen that before. Then I could have stolen from it rather than having to make it up myself. So that's a good source of examples of how to use inline-c. The OCaml people have got the NL interface of Sundials. You want to go look at that? And there's an interesting, slightly opinionated comparison of various solving suites available at this site here. I mean, the guy's written. I mean, I don't think I'm on camera and stuff. Yeah. But he's written a lot of really good solvers in Julia, and has done a comparison of all like Sundials, GSL, various other things, and concludes that his implementation in Julia was the best. So obviously. And there's a video, yes, of Francesco explaining how inline-c works. That's it, really. So.
Can inline-c help you at all with calling Haskell from C? So the other way around?
No, but you can. There's certainly ways of doing that which are. I have done it myself, but I don't recall. Maybe you have to use FFI for that.
I have done this in the past,
Yeah.
but I didn't find it particularly enjoyable.
No, it's not very enjoyable, no. No, I've done that, and I ran into, yes, and then trying to make sure the runtime system is there at link time and all that sort of stuff. Yeah.
So no inline Haskell.
Inline Haskell, yes. No, not that I know of. No, inline-c won't help you with that. This is the idea is you've got a big C package that you don't really want to rewrite.
So you mentioned that it's in H matrix in that package. Does that only contain the two sub-packages of Sundials that you were referring to? Is there still like an open question there for the rest of it?
Yeah, if you want that, then we haven't. The people, and I can tell you who it is. It's a French sort of biotech startup called Nova Discovery. They haven't had any need to use the other packages, but yeah. So we've got an interface to CVODE because we use the solver in there most of the time, but it was easy enough to create the interface to ARK over the years as well. So yeah, and we wanted. I mean, there's some good guys that Nova Discovery who want to use lots more stuff in it. Sometimes because it has got a lot of features.
And also, do you ever wind up with linker problems if you were to use this on new machines? Because it seems like you wouldn't have all knowledge that, I don't know, it seems like there could be some linker issues if you're with inline-c. Have you run into any, or is it pretty clean? The team, I mean, when I've been developing it, because it's all been open, it's very nice to know Discovery, they've made it all open source. So I'm running on a Mac, and I just did brew install Sundials, and everything worked. But the environment I'm working on with the Nova Discovery people is Nix, and so I think I did package up. I might have packaged up Sundials myself, I can't remember now. But Sundials is available in Nix, so if you use Nix, everything will work. And they're also, no, I think that's, it should work in Nix, but it certainly works for me, MacOS, with Brew. I can't see why it would not work on a Linux machine. Great.